Okay.
All right. Hello, everybody. It's a pleasure to have Orko here with us today, who'll be talking about phases and phase transitions of spin chains with non-invertible symmetries. Please go ahead, Orko.
Thank you, Apurv. Thank you, Sakura and Laksha, for inviting me. This has been a great seminar series, and I hope I'll be able to add to all of the interesting stuff that's been going on. Let me get the meeting controls out of the way. Good. So today I'll tell you about some work that I've done with Ömer, who is a postdoc at MIT, and my advisor, Xiaogang. We just put this out last week. This is the first talk where I don't have archive XXXX on the first slide. So good. I'll first start with some introduction, which will be brief because this is a symmetry seminar. I don't need to introduce generalized symmetries too much. And then we'll start with a warm-up example where we discuss how there's a non-invertible symmetry in a very familiar system, which is the 1 plus 1D Ising model. This has been studied by a lot of authors in recent months. So this will also be brief. The main punchline is going to be in these two sections here. I hope people can see my cursor. In these two sections here, where I'll build towards constructing a spin chain type model for rep S3 symmetry. And to get there, we'll first construct a spin chain with S3 symmetry and then do some manipulation to that to get to there. Great. So we all know that ordinary symmetries within this generalized symmetry framework can be thought of as codimension 1 invertible topological defects. Here I'm showing a cartoon where I have 1 plus 1D spacetime, and these defects are one-dimensional, so they're codimension 1. They're labeled by group elements G and H for some group G, big G, and they have group-like composition. So you can compose these defects or bring them close to each other and fuse them to form another one which is labeled by G times H. So this has been studied by all theoretical physicists for many decades, and in recent years people have defined these p-form symmetries which act on higher codimension manifolds in spacetime. Once we quantize such theories, these were described in a spacetime language so far. But once you quantize the theory, you pick a Hilbert space, define a Hamiltonian describing the time evolution of the system. These defects become operators, which again, as I mentioned, they have group-like composition. You can further generalize this to defects that don't have a corresponding inverse defect. These are very creatively named non-invertible symmetry. In 1 plus 1D, if you consider only zero-form symmetries, finite symmetries, they are described by fusion categories. At least that's the current understanding. But in a general dimension, general D plus 1 dimension, if the symmetry is finite, I've been told that this is described by multi-fusion D category, whatever that is. So there is a lot that is understood about the structure of these things. In this particular talk, we're going to focus specifically on this case, the 1 plus 1D fusion category case, and we're going to discuss some very simple examples just to get our hands dirty. So this will not be a very general talk, but more like trying to understand some features in simple examples. Good, so let's focus on non-invertible symmetries. They show up in various contexts, as has been reviewed by these two really good reviews. For many years, people knew about these Verlinde lines in rational CFTs, but in recent years, people have also understood that non-invertible symmetries can give you a lot of mileage, even in non-conformal QFTs. So they, for instance, in adjoint QCD2, they constrain RG flows. Recent work here discussed modifications to crossing rules of S matrices in some integrable theories that have these symmetries. There are also higher dimensional examples, such as the ones discussed in these papers here. I'll not go into these in too much detail, but this is to say that non-invertible symmetries have already shown some payoff, and they're interesting to consider, and they have been considered in field theory, but they have also been considered in lattice models. For instance, in anion chains, starting all the way back in 2006. These anion chains were constructed from as sort of children of non-abelian topological orders. So they're defined as 1 plus 1D Hamiltonians whose Hilbert spaces have the structure of fusion trees of anions. And once you construct these Hamiltonians, they naturally have non-invertible symmetries, and those constrain the allowed phases. There are related examples that were considered in this paper here. They have also been found in 2D StatMech models, again, all the way back in 2016. They give you the ability to compute CFT data from just lattice models, which is great. More generally, non-abelian topological orders in specifically, let's say in 2 plus 1D, they realize spontaneous symmetry breaking phases of these one-form non-invertible symmetries. So these symmetries can spontaneously break, and they lead to exotic phases. So they are just like ordinary symmetries in that sense. They even emerge in ordinary ordered phases, as discussed here. And people have also considered gap phases of these things, including a paper that came out at the same time as ours, by none other than our seminar organizers. So these symmetries have been considered in lattice models. They have a lot of the similar features, and the idea of this talk is to again like construct simple spin chain type lattice models. So I'll get to that in a second, what that means, that give you or show you the features of non-invertible symmetries in a more concrete UV complete setting. Good. So the key takeaways of this talk, if you're going to fall asleep for the rest of the talk, are that we construct a rep S3 symmetric spin chain, starting from an S3 symmetric one, which is more ordinary. I'll explain how exactly. Just to note that rep S3 is the smallest non-anomalous finite fusion category symmetry. So it's a good example to kind of start with. Okay, and we make predictions about their phase diagrams. I'm showing these kind of cryptic pictures here. I'll explain what they mean as we go along. So we label the phases of these spin chains with the symmetry data, and we discuss some duality symmetries, kind of similar to Kramer's one year, which people may be familiar with. And these are what are called intrinsically non-invertible, as opposed to the rep S3, which is known as group theoretical non-invertible. So we'll talk about that as well. With that, let me give a brief explainer of what I mean by spin chain. I really mean this big phrase, but when I say spin chain, it's a 1 plus 1D Hamiltonian defined on a Hilbert space that has a tensor product decomposition with a with a finite on-site dimension. So each factor of that tensor product is finite dimensional. So I want to contrast that with a more general term lattice model, which can be used to mean various different things, such as StatMech models on a space-time lattice. Could mean something like an anion chain, where the Hilbert space does not have a tensor product decomposition. It could also, you could also have a Hamiltonian lattice model with rotor degrees of freedom, for instance, which are infinite dimensional. So I want to rule out all of these and focus on this simple case because one, the tensor product Hilbert space is a natural setting for condensed matter problems. So one may naturally ask if all of these exotic physics can be realized in the simplest or dumbest of settings. And the second thing, the finite on-site dimension, it mostly is a technical assumption. It lets you think of operators simply as finite dimensional matrices, as long as your system is finite but large. So that's the reason we are considering spin chain.
Why do you say Anion chains don't have tensor decomposable Hilbert spaces. In many known examples, including rep S3 or group-like examples, they do reduce to spin chains, right?
Right. In some cases they do. Yeah. I guess what I want to say is that in general they don't have to.
I
Like
see.
in a Fibonacci chain or aka
Sure.
golden chain
I see.
doesn't have to. Yeah. Good. All right. So that's my spiel on spin chain. Let's get started with a warm-up example, which is all of our favorite Ising model. Um, this is the Hamiltonian, where the degrees of freedom are qubits on a chain, and we have these Pauli matrices acting on them. The phase diagram is pretty simple. There are two gapped phases. There is a Z2 symmetry in this system, which is implemented by the product of sigma x matrices on each side. So that symmetry can be spontaneously broken to give a ferromagnet phase, or it's symmetric, or the system is symmetric when H is large compared to J, and you're in a paramagnet phase or in a symmetric phase. And there's a critical point described by the Ising CFT. And we all know that there's a Kramers-Wanier duality transformation, as shown here, which interchanges the two phases. AKA, if I did this transformation on this Hamiltonian, you interchange the J and H couplings. Okay, you have to be careful. You have to be on a periodic chain, and so on and so forth. But with all those caveats, these two phases are interchanged. And really, it's a duality only in the symmetric subspace. So I shouldn't be calling it duality, but that seems to be how the field talks about it. So I've kept that usage. Good. It turns out that you can think of this Kramers-Wanier symmetry at the Kramers-Wanier transformation at the critical point, where the couplings are the same, this coupling and this coupling, as a non-invertible symmetry. In fact, there's an operator that these people explicitly wrote out that implements this transformation, and it satisfies this symmetry algebra. And just staring at these two equations, you can, T is translation by a single lattice site. So staring at these two equations, one can see that this must be a non-invertible operator because the determinant of this operator, so this like exponentially large matrix, the determinant has to be 0 because d times d dagger is a projector, which is a non-trivial kernel. So this is an operator that commutes with the Hamiltonian. It has a non-trivial kernel, so it is a symmetry, but it's just that it's not invertible. Good. So once you're satisfied that this is just like any other symmetry, you may ask, are there any deformations of my Ising model that preserve this symmetry? So one such simple deformation that's two-body Hamiltonian is this Zhelezhinsky-Moria type interaction. Don't worry if you don't know what Zhelezhinsky-Moria means. Just consider this Hamiltonian, and if you stare at this, you can see that this is indeed symmetric under the sigma z going to sigma x and vice versa transformation. Again, this term was considered for other reasons in the literature before. Good. So you add this deformation. It turns out that because all of this is still two-body in the spin language, it is quadratic in the fermion language once you do a Jordan-Wigner transformation, and you can exactly diagonalize this. Great. So this is the spectrum. You can declare victory, but we want to do a bit more. We want to look at the phase diagram. So here's a phase diagram as a function of J and H and lambda as well, but lambda is fixed to be this linear combination of J and H, just to make the phase diagram 2D instead of 3D. The J equals H line is the subdual line or the Kramers-Wanier symmetric line, and at the middle of that, just at the center of that of this interval is where J equals H equals 1 and lambda equals 0. So that's the Ising critical point. And you can deform away on this line, which is the Kramers-Wanier symmetric line. And either side, for either sign of lambda, you get into this large gapless phase, gapless region, which I've labeled as C equals 1, because it has uh, you know, two pairs of left movers and right movers. So good. So you have a C equals 1/2 going into C equals 1 theory. And turns out if you look at, if you stare at the band structures of this fermion problem long enough, this looks like a Z equals 3 dynamical exponent, Z equals 3 transition. These lines are Z equals 2. There's a lot of rich physics going on somehow in this very simple model. And note that once you go away from the J equals to H line at the Ising critical point, that's when you go into the two gapped phases, which are unshaded. I want to focus on a specific part of this gapless region, on the self-dual line specifically. It turns out that there's a eminent U1 symmetry, eminent using the same terminology as these authors here. There's an eminent U1 symmetry, which is essentially the UV translation acting on the Majoranas on the lattice, and it acts as e to the IKF, KF being this Fermi momentum. So it acts as this phase. It acts only on the left movers because the right movers you see are at k equals 0. So there's no phase on these. So they act only on the left movers. There's two left moving modes. They form an SO2 rep, same at U1. Note that their velocities are the same, so it makes sense to combine them into the same SO2 rep. And so this U1 symmetry, it acts only on the left movers, which is why I'm calling it chiral. And the claim is that this is anomalous. You can realize this on the boundary of a quantum Hall state. So that's the anomaly theory. And this, yeah, so there's an emergent, an eminent anomalous U1 symmetry on this line. We haven't worked out the anomaly matching between the lattice and the IR theory, but that could be interesting to look into. And it's just looking at the anomalies on the lattice very naively. There's the translation of the Majoranas has some kind of anomaly. So one could guess that maybe that anomaly and the UV and the IR anomaly of the U1 may be related. But again, let me not say too much about that because we haven't explored that concretely. Good. So that's all I have to say about the Ising model. It's a small deformation of everything that people already know about the Ising model. So hopefully there are no other questions. So let me move on to the spin chain with S3 symmetry. Here I'm going to use the presentation of S3 as a dihedral group of 6 elements where the S represents reflection and R represents a 2π/3 rotation, shown in this cartoon here. So one of the simplest models with S3 symmetry is the three-state Potts model, which is a quantum version of the classical three-state Potts model, which you may have seen in StatMech class. The Z and X here are Z3 clock and shift operators with this algebra. And this has an S3 symmetry generated by this product of X, which implements this 2π/3 kind of rotation on the clock degrees of freedom. And there's a charge conjugation reflection symmetry. So C is the charge conjugation operator, which acts by sending X to X dagger, Z to Z dagger. And it acts, so it's just a cartoon showing that. The phase diagram of this is very similar to the Ising model. There's a paramagnet phase and there's a ferromagnet phase. The ferromagnet phase is threefold degenerate. It turns out that the ferromagnet phase actually does not break all of the symmetries. So for each of these ground states, there's a remaining symmetry, and that is Z2. So you may ask, is it possible to realize symmetry breaking down to nothing from S3? One simple way of doing that is by adding some icing degrees of freedom into the game. So we add these two other terms, which are kind of decoupled from everything else so far. And the claim is that these will let you realize all of the SSB phases. Um, without adding more coupling terms, you'd have S3 times Z2 symmetries. It's more than what you wanted. So you can add some terms that couple the Z2 odd, some Z2 odd operator of the Q-trits with the Z2 odd operator of the icing. And so that's the reason why I add this delta H guy to explicitly break this big symmetry down to S3. Great. So once you've added all of these terms, this this Hamiltonian, my claim is that this realizes all of the phases, all of the symmetry breaking phases that you might expect from S3, meaning spontaneous symmetry breaking down to all of its subgroups. So to simplify life, we first set J5 and J6 to 0. This is coupling terms. And then it's just a pots and an icing. So the phase diagram is simply like this, where you have pots transition as you go in the horizontal direction and an icing transition as you go in the vertical direction. And there's some multi-criticality, which is the stacking of these two CFTs. But because these are gapped phases, you expect them to remain the same. So they don't change when you have small J5 and J6, when you have small couplings. Moreover, the gapless states will also remain unchanged if these perturbations are actually RG relevant. It turns out in this case they are. I'll not go into the details of that, but the point is that this phase diagram remains basically unchanged for small J5 and J6, all of it, not just the gapped parts. There's one more feature that's similar to the icing case, which is that there is a Kramers-Wanier duality, a Z3 analog of that, if you will, meaning that Z3 is not to tell you that this is a triality, but I'm just saying that this comes from kind of gauging Z3 as opposed to gauging Z2 in the icing case. Good, so that there is a closely related duality which acts by sending the paramagnet terms to the ferromagnet terms. You can play the same game. It becomes a non-invertible symmetry at the critical point. But this big Hamiltonian that I just wrote down, which combines all of these things, by itself actually does not preserve its form under this action, simply because you have to do something to the qubits as well. And one simple way of salvaging some kind of Kramers-Wanier is by adding some more qubits. So I label them as sigma and tau. And the way it acts is you do your ordinary Kramers-Wanier and you do a half translation on the qubits. So when you square this guy, it becomes a translation on the qubits. Here's a cartoon kind of showing the Hamiltonian. There's a bunch of different couplings, and you have Q-trits and 2 qubits on each side. And once you have this extended model, there's a relatively large region in parameter space that has the Kramers-Wanier symmetry. So it's not just J1, it's not just J1 equals J2 and J5 equals J6 equals 0, but now you can set that to something non-zero, but you just have to make those two couplings also equal. You can study this phase diagram using some numerical techniques that people developed about 15 years ago. I'll not go into the details of this, but if people are interested, I can talk about that offline. So we're going to plot the ground state degeneracies and the central charges as a function of J1 and J3, setting J2 and J4 to 1 minus J1, 1 minus J3, respectively. And yeah, once you look at this color map closely, you see that indeed you realize 6-fold, 3-fold, 2-fold, and 1-fold ground state degeneracies. So those are your four predictions from analytical arguments. And there are some phase transitions. The value of the central charge, if you look closely enough, is off. Like you expected a Ising transition here, but you're getting some 0.2 or something like that. This looks pretty haphazard. There's different values at different places. So this has to do with how the central charge is extracted in this algorithm, and we're going to remedy that in a second. But before that, let me tell you what happens when you turn on this J5 and J6 terms, which get turned on when theta is non-zero, this theta parameter. So as you turn on theta, you go into firstly, for small theta, the phase diagram remains the same, which is what we predicted based on RG arguments. But at large enough theta, it turns out that there's this big gapless region where central charge is non-zero. So that indicates that it's a gapless region. There are some indications that this is also an incommensurate phase. So let's get to that in a second. But yeah, so that gapless region shows up on the on the J1 equals J2 line, which is where the Kramers-Swannier symmetry, Kramers-Swannier transformation becomes a symmetry. So this is Kramers-Swannier symmetric gapless phase. Even though this symmetry is not really exact away from this line, but in some sense it's in some sense it's like emergent near that line. So before we get to that, I just want to mention that you can compute the central charges using a different technique, using what is known as the entanglement entropy scaling. And you can actually extract pretty accurate values of central charge from this. On this line, it's close to 0.8, which is the central charge of Potts. As we predicted, this is a Potts transition. And on this line, it's very close to 0.5, which is the central charge of the Ising CFT. That gives you some evidence that indeed these are the transitions that you expected them to be. And you can do that, for every point on these lines and convince yourself that they are indeed Ising and Potts CFTs. And you can even do that at the multi-critical point, and you get a central charge of 1.3, which is the sum of 0.8 and 0.5. So indeed, it is the stacked CFT of Ising and Potts. Another thing about this gapless region is that you can compute the expectation value of sigma z, which is the Ising order parameter. And when you do this on an open chain, it's expected that you get some oscillations because of the boundary condition. Kind of heuristically, you can think of the boundary condition as like a defect of the Ising degrees of freedom. And because the Ising degrees of freedom are ordered above this line, there is some oscillation in that order parameter. And when you compute the Fourier transform of that, you get peaks if you have any oscillations. And it turns out that the position of the peak is very sensitive to the parameters. So here I'm showing you with J3 equals 0.55, which is somewhere on this line here, with two different values of J1, which is the horizontal axis. Two different values give you two different peaks in your Fourier transform. So that's an indication that there is a smoothly varying wavelength for this oscillation. And that is kind of similar to how in the Ising case, so I'm drawing some analogies here. In the Ising case, when you deformed away from the Ising CFT with this self-dual perturbation, it took you into this large gapless region, which we showed had this smoothly varying KF, this Fermi momentum, which will characterize this kind of density oscillations. In this case as well, you see a smoothly varying. I only show you two data points, but I guess you have to trust me on this. But if you smoothly vary J1 and J1 within this region, or even J3, whatever, you get different oscillation frequencies. So this is with this analogy, you may also, if you take and run with this, you may even make predictions about an eminent U1 symmetry in this region, similar to the Ising case. And maybe that can be made more precise. Note that this line here also has Kramers-Swannier symmetry, just like in the Ising case. So maybe that analogy is not too far-fetched, but we haven't made that too much more precise at present. Um, so before I move on to the next section, let me see if there are any questions. Oh yeah, Hotat.
Yeah, Arkya, can you go back one slide?
Yes.
Um, yeah, so in the bottom figure, what is the color? What's the meaning of the color?
Do you mean like sorry, this?
Oh, yeah. What's the meaning of the color in the top and the
Oh yeah. Yeah, all of the blue, dark blue is basically gapped, so it's giving you a central charge of 0.
Oh, I see. So the color is the central
Yeah.
charge.
Yeah, the color is, yeah, exactly. This is central charge, this is ground. Sorry, I should have labeled that.
I see. So in the last figure that you shown, why there was this stripe things like
Good. Yeah, I didn't explain this. I kind of glossed over this. So the central charge is extracted by doing this tensor entanglement RG scheme where you discretize your partition function associated to this Hamiltonian, and you do this like zoom out operation. And once you do this enough times, you get a fixed point tensor, and you look at the largest eigenvalue of that tensor. And that largest eigenvalue has the central charge in a kind of um, 1 over L term, where L is the effective system size. Excuse me.
Mhm.
Um, so if so that 1 over L term, you do system size scaling on that for different systems. So for different number of iterations of the RG, your effective system size sort of like differs by factors of 2 every time. So you do that for different iteration steps, effectively doing system size scaling, and you can extract that number. But it turns out that number has a coefficient, which is the velocity of
Oh,
the gapless mode, which because this, it depends sensitively on the lattice parameters on like J1, J3, and so on. So that velocity changes throughout that region, presumably. And so extracting the central charge is tricky because you don't know what that velocity is. That's one reason. Another reason is that because it has a 1 over L dependence, if your velocity is sort of not like commensurate with the system size, once you like double, quadruple your system size, um, your finite system sort of picks up um, wildly different values of that velocity. And so whenever you extract the central charge with that velocity, um, you kind of uh, you kind of also pick up that system size dependence.
I see. So it's a numerical artifact. It's not.
Yeah, exactly. So I want to say this is a numerical artifact. In fact, it shows up even in the icing case. If you did this tensor, I didn't show you that because it was exactly solvable. But even in the icing case, if you did this tensor RG thing, even there, you have these stripe features showing up.
I see. And in the top figures, why in the middle regions it's red? Are you saying there's a lot of ground? Like, oh, sorry, in the top.
This one,
Yeah,
this one
that's
you mean?
yeah.
Yeah, whenever the system is gapless, you shouldn't trust the ground state degeneracy too much because, you know, it might think of, 1 over L separated states as just ground state or,
I see.
a part of a degenerate ground state manifold. Whenever the ground state manifold is separated by some like order 1 gap, then you can sort of trust the ground state degeneracy, which is in these phases.
Mhm.
Yeah.
I see. Thanks.
Yeah, no problem. Thank you.
Yeah, maybe I like to add that this stripe indicate incommensurate phase. So this is a sign to identify incommensurate phase.
Yeah. Yeah.
Yeah.
Thanks, Sharon. Yeah. We actually seen that in many different examples. So that that is that's why it's a pretty reliable signature, numerically. And yeah, it's also in addition to this Fourier transform data, so they're all consistent, and that's why we feel pretty confident arguing that it's an incommensurate phase. Okay. Great. So let me move on. So we constructed this S3 symmetric system, which has self-duality, all of this rich phase diagram, and so on. We want to now take that and gauge the Z2 subgroup of S3. And it turns out that this actually gives you a rep S3 symmetric model. Maybe I'll come back to that in a couple of slides. But just operationally, you can do this gauging of this Z2 symmetry, meaning the Z2 symmetry generated by this operator here. And to do that, you couple in background fields, do minimal coupling, impose Gauss law, gauge fix, and so on. You get a dual Hamiltonian, which looks kind of gross. So I'm going to cover it up. But the point is you can do this transformation, this minimal coupling, etc. You can do all of that with all of the terms that we had in the previous S3 symmetric model, and that gives you another spin chain model. And you can ask, what are the symmetries of this model? There is an invertible symmetry that's generated by the product of these mu x's. And there's a non-invertible symmetry that's generated by this kind of MPO symmetry, or matrix product operator, where the matrices are given here. They depend on the qubit and qubit degrees of freedom. This is some detail, but the point is that the symmetry algebra actually matches that of rep S3. So this one is labeled by the sign rep of S3, and this non-invertible guy is labeled by the 2D rep, which I labeled with 2. And their algebra matches the fusion rules of the irreducible representations of S3. And so indeed you get a rep S3 symmetric Hamiltonian. Since our original Hamiltonian had some self-duality operator, once you gauge that operator, so you do the same minimal coupling game, you get a new operator, which I'm calling D sub rep S3. And this new operator also implements some non-invertible symmetry in some corresponding self-dual parameter manifold. And it has this symmetry algebra, which is very similar very similar to the one that we already had for Z3. And it implements these operator maps. So it maps the terms of the Hamiltonian back to itself, just like a Kramers-Swannier duality would do. And it interchanges some couplings. So like this was our J1 term of the new Hamiltonian. And this was like a J2 term. So J1 and J2 couplings get interchanged. So that in the end will interchange some gapped phases of your new model. And so it is a duality, and you'll have self-dual critical points between those phases. So here's a gauging web that sort of captures all of the stuff that we've been talking about. You had an S3 symmetric model, which I'm labeling with the fusion category Beck S3. You can gauge subgroups of S3. So for instance, if you gauge Z3, it's a self-duality, which is this gauging here. You could gauge the entire group that you may believe that gives you rep S3. But it turns out that if you gauge by just the Z2 part, as these authors showed, even that is enough, you get to rep S3. So this is the one that we've been using, this transformation. On the rep S3 side, there's some gauging that actually gives it back, which is gauging by this algebra object. An idea, again, introduced by these authors, at least to my knowledge. And we claim that our D-rep S3 is a way to implement this gauging in our lattice model via a sequential circuit, which is sort of borrowing some ideas that these authors here developed about transformations that map different gap phases associated to a particular symmetry to each other. So in that sense, this is indeed a sequential circuit that maps different phases of a rep S3 spin chain model. On the other hand, if you gauged by either the regular rep object or this kind of like a Z2 object, you go back to vec S3. And this direction we haven't explored in our work, but it's I think it's a straightforward straightforward thing to do. At least this part is pretty straightforward. I don't know how to gauge by a regular representation. Okay. So we can look at the phase diagram of this new model, and again we set J5 and J6, these kind of ugly terms, to 0 for simplicity. And the phase diagram is very similar to the S3 case, which is what you might have expected because vec S3 and rep S3 are Morita equivalent. So you might expect that all of their gap phases sort of match 1-to-1 with each other. And because the two models are related by some kind of topological manipulation, the gapless phases also remain largely the same. Maybe they get orbifolded, but the low energy description is almost exactly the same. So I've labeled them with these Hodgsonizing CFTs again. Maybe then one interesting thing to look into is what are the different symmetry breaking patterns. So for instance, you have this unique ground state in the rep S3 symmetric phase, but you have these other phases. For instance, you could have a phase that breaks just the W2 transformation, and that is this one. So it is symmetric under this invertible Z2 guy. That's why we label this as rep S3 mod Z2. I should have added a citation here, but okay. You also have a phase where the W1 prime, this Z2 operator, that symmetry is spontaneously broken. So we're calling it a Z2 SSB. And you have two ground states here, which are symmetric under W2. And you could have a phase where all of the rep S3 is broken. Both the symmetry generators act non-trivially on the ground state space. Perhaps one curiosity is that on the right half of this phase diagram, you have an Ising CFT separating two gap phases which have the same ground state degeneracy, which may be kind of weird. But it's possible that some part of the ground state manifold just remains gapped, and the other states somehow participate in this low energy theory. Yeah, it's not clear exactly how the details of this work out. But we've done numerics on this. All of this phase diagram is consistent with numerics, which is shown here.
So I have a question.
Yes.
In the previous slide, do you know what is the operator at between these three ground state phases that drives this transition in the Ising? So this is C equal to half, right?
Yeah, this is C equals half, exactly. I mean, you mean at the level of the CFT, or?
Yeah.
Good. That's a good question. I mean, I think the J3 term just flows to the energy primary in the CFT. So I would guess that's the one, but yeah. The only reason I'm a little confused is that this is like Ising orbifolded, so there's some identification between different operators that I'm making. So I'm not 100% sure about that. Yeah. Yeah, I don't have a very good answer.
Thanks.
So I thought it's two copies of Ising. So there are two degenerate Ising CFTs, and then you have a combined operator.
So in our model, at least, the central charge is definitely equal to 1/2 and not 1, which is what you would expect if you had two Ising CFTs stacked onto each other, which I don't know if that's what you mean. Maybe you mean something else.
I don't mean stacking, but rather
Okay.
two universes or two gapless states which are degenerate, and both of them have Ising CFT.
Yeah, that is possible actually. Yeah, that is not ruled out by this C equals 1/2. That's right.
We discussed this, no? There are
Yeah.
basically these two Ising models, Ising plus Ising, and that's consistent with your C equals to half.
That's right. So see,
And so
yeah, if
from
you can
general
compute this.
grounds, right, you would get this Ising plus Ising story.
Yeah, I think, right. So I think what you're saying, if I understand that correctly, correct me if I'm wrong, you mean that there's some like degeneracy at every level in the low energy theory, where there's like two states, there's like degenerate states at every energy level, in like the low energy theory on this.
Yeah.
Okay.
Yeah.
Yeah, we haven't looked into like the energy spectrum at all. Because these were with like pretty large systems, like L equals 100. You can't really do exact diagonalization on them. So we haven't looked into the excitation spectra. There are techniques to do it, but we just haven't looked into it.
And I think that
Yeah.
similar remarks also hold for the earlier systems that you discussed, like the S3 one.
That's right. Yeah. So these phase diagrams should, be exactly the same, which is kind of what I'm trying to argue. So it should also, yeah, exactly. It should also apply to the S3.
Okay, thank you.
All the low-lying states, including the states corresponding to the primaries in the Ising CFT, should have a twofold degeneracy.
I see.
And I think this the operator would send one to like a trivial plus ferromagnet on one side and the opposite on the other side. So you get three ground states on both sides of the deformation.
I see. I see. Okay. Okay, yeah. Let me just say that I haven't thought too much about that, but sounds consistent with what we've seen. Cool. Yes. Okay, good. Just labeling the phase transitions again. I'm not showing the numerical computation of central charges, but we've done that and those match these CFTs. And I want to say that this, matches with the expectation that gap phases of fusion category symmetries are in one-to-one correspondence with module categories over them. In this case, for rep S3, there are 4 of them labeled by rep H, where H is a subgroup of S3. There's 4 of those, for conjugacy classes of subgroups. Let me say that. And yeah, so these 4 phases are in one-to-one correspondence with them. We also discuss order parameters in our paper. So for ordinary symmetries, you could compute 2-point functions of order parameters, which are local operators, and they detect SSB phases. It's also a related notion of a disorder parameter, which comes from restricting the symmetry operator to a patch. So more generally, you can consider these patch operators. So for S3, the order patch operators, the charge patch operators, they have a trivial bug. So you just have local operators at sites J and J plus L. But the disorder patch operators are these string-like operators coming from restricting our symmetry operators to finite patch. They're labeled by conjugacy classes, so we've summed over the different generators within a particular conjugacy class. Same for the order 3 guys. And you can do the gauging map that we did earlier to get the rep S3 patch operators.
Sorry,
and
can I ask a question?
Yeah.
In the previous
Yes.
slide, what is this CZ3? C sub Z3?
This is good. So this is like a Z3 charged operator. So you can see that this whole thing is Z2 symmetric under the charge conjugation.
But S3 has so there's one charge which is which transforms under the one-dimensional sign representation, the other which is two-dimensional, right?
Right.
So what representation label does this carry?
Good. Yeah, this one's the charge rep.
Yes.
But this one's kind of weird. Yeah, this is not labeled by not labeled by the 2D rep.
I see.
Yeah, I'm kind of combining, let me think. Yeah, it's kind of like a how do you call it? The restricted representation for just the Z3 part. Like you take the 2D and you restrict the Z3 part, and that gives you the phase and phase star or something like that.
I see. So you're like taking one element of this 2x2 matrix effectively, and it's conjugate on the other side.
Yeah, in that, yeah.
Because under the full S3, this Z operator would transform into something else, right? Would not.
Oh yeah. So for instance, under the charge conjugation, this just Z goes to Z dagger,
Right.
goes back to itself. But because I've added the Hermitian conjugate, this whole thing is neutral under the charge conjugation.
I see.
So it only kind of captures the Z3 SSB. But whenever the Z3 is spontaneously broken, this would become, the web of this would become one. That's kind of the, yeah.
So you've taken like a Z2 orbit inside S3 and constructed.
Right.
I see.
Right. Yeah, I think maybe more generally, you'd want to actually take the irreps and try to construct patch operators for those. I think that's the general strategy.
Yeah, those operators act within the symmetric subspace. So that's why it have a kind of strange form. Because it act within the symmetric subspace. So under duality, when you go to from S3 to rep S3, they would map accordingly.
I see. So you're taking Z2 symmetric operators because you want to study the gauging.
Yeah, exactly. So they act within the symmetric space. So under gauging, they behave nicely.
I see. Thanks.
Yeah, actually, this is also Z3 symmetric, right? So this is actually symmetric under the entire thing. Right? Both of them are symmetric completely, as Shevang was saying. Yes.
Sorry, related question. So
yes.
Should I label the order patch operators by group elements or conjugacy classes? The top one.
Oh, the order patch one.
Yeah.
I think more generally you want to label them by irreps, as Apurva was saying. So yeah, in this case, I just wanted to. This is maybe not the best, not the most general way to label it. This is just to say that this detects Z2 SSB, whereas this thing detects Z3 SSB. That's what the label means.
I see. Okay.
Yeah. Yeah, you can take, so as I was saying, you can take those operators and you can do this gauging map, and you get some new operators. And it turns out that, okay, the disorder patch operators kind of look similar to what you would have expected. They're like restricted symmetry operators. So this corresponding to the 1 prime, this corresponding to the 2. The charge patch operators, on the other hand, they get a string attached to the endpoints. So the 2 endpoints are no longer separated by a trivial string, but there's some string operator acting on the qubits in between. That's true of both of them. So that's maybe a new feature for non-invertible symmetries. And you can check that they have the correct kind of webs for all of the different phases. So for instance, in the rep S3 symmetric phase, you have the disorder operators having a non-zero vev, whereas the order operators have a trivial vev. So there's no SSB. On the other hand, for the rep S3 SSB phases, the rep S3 SSB phase, the ground state manifold is 3-dimensional, and all of the states have a non-trivial vev for the charge type or order type patch operators here and here, but the disorder ones are trivial. These are computed, I should mention, at some fixed point limits. They're pretty clean, but in general, they won't be this clean. All I can say is it's either non-zero or zero, away from those fixed point limits. Okay, this is just to check that indeed these are working as you expect. Okay, and the last piece of our story is about the
Excuse me?
Yes.
Oh, this is Sal. I'm not an iPhone, by the way.
Yes. Yeah.
Can you go back 2 slides when you're showing the string operator? So I was just curious. So with the S3 string operator, it has like a trivial invisible bulk. And if I send one of the points off to infinity, I'm left with like the charged local operator.
Mhm.
But here, when I send one point off to infinity, I'm left with a string operator. I was wondering if it's obvious how that string operator is related to the charged local operator.
Sorry, what do you mean by charged local? Oh, sorry, I see.
Like
good.
OX in the first line.
Yeah, good. So this kind of breaks this interpretation, I think, is what I was trying to argue. But maybe another way of answering this question is that you can think of the endpoints as this O, but there's some string that you need to make the whole thing quote unquote gauge invariant. So if you didn't have this operator would actually not be symmetric. It would not be a symmetric like patch operator. Same for this guy. You have this like gross looking thing in between the mu z. But without this, you wouldn't, this whole thing wouldn't be a symmetric operator.
I guess I was wondering if so if I send X to infinity in the first line, I'm just kind of left with O of Y, right?
Mhm.
So I was wondering if you did the same thing here, like you send J to infinity. If that like string that you're left over is maybe related to the local operator that's under like some
Oh,
rep
yeah.
S3 symmetry transformation or something like that. But I don't know, so I was wondering if you knew.
Yeah, they're probably, they're probably related.
Okay.
I mean, in a very like pedestrian way, like if you just look at this operator near this endpoint, if you do the like the transformation associated to let me think. So associated to W2, the Z and this string would transform in opposite ways, I think. Let me think for a sec. That's true. To like sort of cancel off some transformation. But yeah, that's a good question, and I don't have a general way to think about it. But yeah, so the naive thing would be to say that you send OY to infinity, you're left with some local guy and attached to some string, which goes off to infinity. That's what it looks like. I don't know if that answers the question. Yeah.
In a sense, the words order and disorder are swapped, right, on this slide, because you start with order and disorder, then you gauge some symmetry. So operator that's bilocal and carries two charges separated by some length on the lattice maps to a symmetry string, which is now a disorder operator. I mean, you're not gauging the full symmetry, but loosely speaking.
No, you're totally right, and I was kind of brushing that under the rug, but this thing comes from the order, like Z2 order patch operators from this one.
Yeah.
So indeed, there's some swapping going on for at least these two.
And from that point of view, it makes total sense that there's a symmetry string attached to it. I mean, even Kramer-Vanier has that feature.
For this one indeed, but for the 2D guy, it's less obvious. So yeah, right. Yeah, maybe this one indeed maybe less counterintuitive.
But by order here, you mean you are detecting some symmetry breaking.
Exactly. So the order parameter, yeah, good. So the order ones are non-zero whenever the corresponding symmetry is SSB.
Because say like for SPT phases, you can have a string order parameter, and I guess there you're not measuring a symmetry breaking of something, right?
Right. Yeah, I don't have any comments about the SPT case. But yeah, that is a similarity with the SPT case, but I think those are not related, but I may be wrong about that.
Yeah, I'm just wondering whether in that case you're supposed to call it string disorder rather than string.
Oh yeah, I think right. So in the SPT case, I think you end up having like something like a disorder patch operator, but you make some modifications near the endpoints. Is that correct?
Yeah. I just find it curious that here is order, but it still has a string.
Oh yeah. Yeah. It's exactly. Yeah. good. I think I'm over time, but I have like two slides on the SimTFT, if that's okay.
Yeah, it's totally fine. No worry.
Okay, great. So if you're just considering the S3 and the rep S3 symmetries, the SimTFT description is of this S3 quantum double. But you may ask, what is the enlarged symmetry when you're on the self-dual manifold of parameters? So from the SimTFT language, the S3 quantum double, it has some anyon permutation symmetry, and from this interpretation of this one higher dimensional bulk, we expect that anyon permutation symmetry is related to this duality, self-duality of the spin chain. So if you want to get the SimTFT of the self-dual spin chains, you want to gauge this automorphism. And in this paper, depending on some additional data, the authors suggested either of these two options. JK4 is a Jones-Kaufman theory at level 4. Please don't ask me what that means. So there are two topological orders, and there are two choices. We know we know all of the topological data for both of them. So the question is, which one is it? It turns out that this option leads you to a gapless boundary theory from the SimTFT, which is consistent with a pot CFT and has a symmetric relevant perturbation, which is inconsistent with the phase diagrams we had. Whenever we had pot CFTs, they were restricted to the self-dual manifold. There was no relevant perturbation out of that. That also is consistent with self-duality. So this one's inconsistent. The only consistent one is this JK4 stacked with its 10 reversal. So taking that, you can construct the gap boundaries of it, and it turns out there's just two, and those two indeed correspond to the symmetries of the self-dual S3 spin chain and the self-dual rep S3 spin chain. And then once you've
Sorry, I'm
fixed your symmetry
confused. How is this
Oh, yeah.
consistent with general symmetry considerations? Because there are obviously more gap boundary conditions. Because you can, gauge like a rep S3 mod Z2 or something. So a
Sorry,
full
which one?
SimTFT should really capture all possible, gap boundary conditions you can reach by gauging. There are, not just these two.
Oh, you mean on this slide, right?
Yes.
Okay. Good.
In what sense is this a SimTFT?
I thought that. Sorry. So I thought that.
I mean, the SimTFT, right? You could just say it's the Darker-Witten theory for S3, and then you could say, well, you're really interested only in the topological defects of it, and that's the Drinfeld center. So I'm actually not sure what this JK4, what the role of that is, but if it's a SimTFT and you're only getting two gap boundary conditions, that doesn't sound right. You showed us four gap phases.
Sorry. Let me see. So the four gap phases, they break the subduality symmetry. All of them break the subduality. So those phases are not the phases that so on those parts of the phase diagram, you actually only have S3. So to discuss those parts of the phase diagram, you'd only use this part, this SimTFT.
Okay.
Once you have this additional symmetry that's only on that one line.
I see. So this is so the enriched SimTFT. This is the extended one. Okay, got it.
Exactly.
Yes, thank you.
Yes. Yeah. Sorry, I was a little too quick on that, I guess. Yeah, good. Thanks for pointing that out. So this is only on the vertical line in my phase diagrams, if you remember from half an hour ago, maybe. So on that vertical line, the only gap phases are the first order transitions that you can have between the different S3 SSB phases. Those are the only ones that are, it's only on that one line where you have the self-duality. Because of that self-duality being anomalous, you can't have a trivial gap phase on that line. So the only things you can have are those gapless phases that I showed you, or gapless, states that I showed you, or these first order transition type phases. first order transitions between S3 SSB phases, I should mention, or rep S3 SSB, if you're in the rep S3 side of the duality. And there are also non-Lagrangian algebras, which we've listed in the paper, but we haven't done too much with them. They should label different gapless phases consistent with this enlarged or enriched symmetry. Good. So that's my talk. Here's some conclusions. We argued that non-invertible symmetries exist in pretty down-to-earth kind of spin chain models. And we showed how to get from an S3 spin chain to a rep S3 spin chain by doing some manipulations. And we discussed the SymTFT for the self-dual spin chains. Here are a couple of future directions. One thing that I'm particularly curious about is whether this kind of Kramers-Vanier type engaging duality defect symmetries can be made completely internal, meaning if you don't want them to involve lattice translation in the UV models, can that be achieved within a spin chain type setting? Or is there some kind of obstruction that's some kind of deeper obstruction in that? And with that, I'd like to conclude my talk. Thank you for your attention.
Thanks, Orko. So if there are any questions, please go ahead.
I think that's Sal.
Sal, yeah.
Okay. Yes. Thank you for the talk, Arko. One question I had is this incommensurate gapless phase. Do you know if you can understand that using the SymTFT? Like you said, you had these 6 non-Lagrangian algebras.
Right. Good question. We haven't thought about it. It should, I mean, okay. Because it's a gapless phase, it should, if I believe this whole SymTFT correspondence between the boundary, 1 + 1D theories and the gap or gapless boundaries of the SymTFT, they should be labeled, it should be labeled by one of these. And once you find that label, it should be consistent with a U1 symmetric CFT. It's something I didn't show here, but you can estimate the central charge for that region. It's pretty close to 1. So you might expect some compact boson type CFT to describe that. So whatever that non-Lagrangian algebra is, it should be consistent with such a CFT. Does that address the question?
Yeah. So so your guess is yes.
Yeah, I think it can say some things about it, but not everything, I guess.
Okay. Yeah, I guess one reason I ask is usually when I think of the gapless boundaries of the SymTFT, I'm usually thinking of critical points, not of like these entire phases. So yeah,
I think good. So I think in recent years, at least, people have identified these gapless SPTs, which I would have thought it's a phase, at least in some cases. So it's not necessary that it has to be just a phase transition, I think. Yeah.
Do you know what the reduced topological orders are for these non-Lagrangian algebras?
Yes, we have that in the paper. I just haven't listed them here.
That should then tell you, at least give you some
exactly.
guess using this club sandwich construction.
Yeah, we have like a list of reduced TOs, and we can do this whole game with those as well.
So Matt has a question. Please.
Yes. So could you comment a bit again about why this SU2 level 4 doesn't work? So I guess they differ by.
Yeah. Let me go back to the
H3 class when you gauge.
Yeah, let me just go back to this phase diagram maybe. Yeah, so this is the line on which you have the self-duality. Also for non-zero theta, you also have self-duality. So all of these phase diagrams have this self-dual subduality symmetry on this vertical line here. And on this vertical line, you have Potts CFT, that's the claim. You also have a multi-critical higher central charge thing here, but okay, you do have a Potts, and any relevant perturbation of that Potts actually breaks the subduality, so takes you in these horizontal directions. So that is inconsistent with the SU2 level 4 case, because there, if you try to construct these like boundary gapless theories, you get Potts theories, but all of those solutions have, you get Potts type solutions, but those all have a relevant symmetric deformation, symmetric under this subduality, which seems to be inconsistent with what we see in our model. So yeah, that was the reason. But you said something about an H3 class. Not sure.
Right. I guess these two differ by an H3 class when you gauge the Z2 in the ball. Is that correct?
I don't know how to think about it from that point of view. But I know that this, like the the modular data is different for the two theories, even though the list of anyons and the fusion rules I think are the same. Maybe that's related to what you're saying.
Right. It's like, I think it's sort of like whether you stack Levin-Gu before you gauge the Z2.
Oh, right. Yeah.
The
Okay, that's
E-duality
okay.
of S3.
I see. Yeah. I think that's right. Yeah.
And I just want to understand if it's related to that, as in whether you're allowed to condense the flux or not, because if you stack by Levin-Gu, then one of the flux becomes a semyon, and then you're not allowed to
I
condense, so
see.
you get
I
less
see.
boundaries.
Yeah. Good. Yeah, I think that's right. Yeah. Yeah, I think that's probably right. So you get some relevant perturbation sitting in the flux sector of the SymTFT resolved partition function, if you know what I mean.
And I had another unrelated question, which was when you were talking about gauging on the lattice, you said you didn't know how to gauge rep S3, but can't you just do that by gauging rep Z3 and then Z2 or something?
Yeah. So yeah, when I showed that figure, I should have just said that. Exactly. So when I showed you that the thing, yeah, you could just do them. You could just do
steps, right?
Yeah, two-step. Do this first and then do this. That's right.
Mm-hmm.
And that is kind of like dual to the way I would gauge S3 as well, like gauge Z3 first and then Z2. Right.
But the thing you said you didn't know how to do was what again?
I guess I don't know how to do this directly. Like, I don't know how to do minimal coupling, for instance, for algebra objects. I know how to like, I know how to insert defects for ordinary symmetries, like Z2, maybe even for S3. I'm not sure how to do like a gauging by an algebra object, a general algebra object for some general fusion category on some lattice model. But
So
okay,
I think maybe
getting...
Yanyon chain, we do know this, right?
Yeah, in the Yanyon chain.
So there it is a lattice model in some sense, and there we do know it by changing the module category.
Right. Yeah, I just wanted, good. I want to say that I don't know how to do it in a spin chain. Let me say that. Yeah, I kind of want to argue this thing that in general, I think such a gauging map can always be realized by some sequential circuit type thing, because such a gauging would take you from one gap phase to another. And the thing that people have, Nat and you guys have argued here is that maps between different gap phases can be generally implemented by sequential circuits. So that's my guess for the general case, but I'm not 100% sure about it.
I guess that only makes it well defined only if you come back to the same symmetry, right? Like if you go between them, there shouldn't be a sequential circuit.
Right. This is for like self-gaugings, exactly. Yeah, for these ones, I'm not sure.
Are there any more questions? Okay, if not, thanks very much, Orko. Maybe we can turn the recording off. So could you send me the slides so I put them up on the...
Yes, I'll just email it to you.
Perfect.